discussing the proof of the calculation of the Mab invariant of AP3, and we have to finish the proof over here. So I ended with the model. So let me just recall what's the situation in the model case. So we start with RP3 with the standard metric of constant curvature 1. So here I'm identifying antipodal points. Right? This is quotient by an equivalence relation given by the antipodal points on the boundary. Then we use the Green's function. So we choose a pole, let's say the north pole over here. We did a conformal deformation of G0 using the Green's function with pole which goes to plus infinity at the north pole, and then we got this asymptotically flat manifold which is rotationally symmetric and is, so again the boundary, antipodal points are identified in the boundary. I call this LS, and this is half Schwartz. Right? So that's what we did. So this is a rotationally symmetric manifold. We can consider the inverse mean curvature flow over here, which is just given by the leaves with the appropriate choice of time. So this is going to be, for example, sigma of t, where sigma of 0 is the boundary. And in the level set formulation, this guy is going to be the set of points where some function phi is equal to t. Then, because of the rotational symmetry, we also consider the function that realizes the Sobolev constant, right, which comes from doing the inverse procedure. So this is a function u0 of x, which is rotationally symmetric over there, and satisfies that the Sobolev constant, in other words, the gradient of, with respect to G bar AF u0 square divided by integral to u0 over 6 to the power 6, the power 1/3. This is equal to sigma 2 over 8, which is just the Sobolev constant of that manifold over there. Right? And because of the rotational symmetry, this function u0 is going to be constant over sigma t. So this function I define to be f of t. By definition, is the value assumed by u0 on sigma of t. So this is a solution to inverse mean curvature flow. And if you want, equivalently, this is saying that the function u0, remember that the time t is just the value assumed by the function phi. So u0 is just f composed with phi. Right? So now the idea is that we want to consider a general manifold, asymptotically flat manifold, and we want to estimate the Sobolev constant. So we need to construct a test function. So the test function is going to be something like u0 over here. So what you do is that you consider the inverse mean curvature flow over this general manifold. This gives you the phi, and then you just plug in the same f that we had in the model case. So that's going to define a function that I will use to estimate the Sobolev ratio. Okay, so this is the model case. So in general, I want to consider some metric on RP3. Right? You can do the same. You can do the same procedure, right? So you can blow up a point with the Green's function, so you get an asymptotically flat manifold. Let me just do something like this. This is an RP3, right? And this guy is going to be diffeomorphic to to RP3 minus a point, the point that I chose to send to infinity. Right? So now I have this asymptotically flat metric on RP3 minus a point, which is a scalar flat because of the choice of the Green's function. And I want to prove, so what we want to prove is that the Sobolev constant of this metric is at most sigma 2 over 8. Where the Sobolev constant is just the infimum of these ratios over all functions. So that's the situation. So let me say something. So when you consider the Sobolev constants of non-compact manifolds, right? Usually you consider compactly supported functions in the definition. But because of the asymptotics, you can actually see that this is not necessary. You can use as test functions which decay sufficiently fast, which is the case of U0, for example. So U0 doesn't have compact support, but it has the right decay, so that it is a valid test function for the Sobolev ratio. So that's an important observation. Okay, so let me sketch the proof then. So how do we do this? Right. Okay. So now we have this manifold over here, and we want to construct a foliation given by inverse mean curvature flow. So first, it follows by results of mix Simon and Yao. This is a very classic, very well-known paper in the 80s, I guess, over the existence of minimal surfaces in three manifolds. So it follows from the techniques of their paper that there always exists, given any asymptotically flat manifold, right? So I'm working with GAF here on RP3 minus a point, something like this. So there's always exists an outermost minimal surface. So outermost just means that outside the minimal surface there are no others. So it's the sort of like the last minimal surface that you can find in your Riemannian manifold, which is, in this case, it will be diffeomorphic to, let me not put in this way. This is going to be a disjoint union of what I will call weakly embedded two spheres. So weakly embedded here is just means that it's the limit of embedded surfaces, of embedded spheres. So think of this example, right? When you have over here, this is a minimal surface which is actually a projective plane, right? But if you just go a little up, you get something which is precisely a sphere. This is a projective plane, but which is approximated by two spheres. Right? So the idea is that in their paper they consider the problem of minimizing area in the isotopic class of a given surface, right? And you can see, well, it follows from the results in the paper, that if you start with a sphere, so the genus can never go up. If you start with a sphere and minimize area in the isotopic class, maybe you get a disjoint union of minimal surfaces, but they all have to be either spheres or projective planes. So the projective plane happens, for example, in this case. Okay, so that's a classic stock from minimal surface theory. So now the point is that you can choose one of these components and start the inverse mean curvature flow with that. Because of the condition of being outermost, right? This fits into the theory that I just described of Huisken and Newman. that the boundary has to be what I called, well, I assume that there must be no other minimal surfaces inside the given manifold. Right? So I didn't talk here, I didn't explain here what do you do if you have more than one component of the boundary. Right? It's actually possible to, you fix one component, evolve it, and sort of the flow sort of like swallows the other components over time. But let me just focus, just to give the idea. Let's suppose that it's just one component. It's pretty much the same thing. So the drawing could be, you could have something like this, right? A minimal projective plane, for example. Or you could even have something like this, where there is a smaller minimal surface, which is really a sphere. It could be also like this, and you have a sphere over here. But anyway, you pick one of these components of the boundary, sigma of 0, and a component. And then you use Huisken-Illmann theory. To produce an inverse mean curvature flow. Sigma of t is going to be the boundary of the set of points where a function phi is less than t. This is going to be a weak solution to inverse mean curvature flow. So there is a function phi which is proper and locally Lipschitz. Such that this solves the flow and has this initial condition. Right? So that's maybe the function could be, for example, negative over here, but it will be positive in the region outside the initial condition. Okay, so what you do then, we have the function phi. Now we just have to transplant the f that we found in the model case. So the definition of my test function would be just u. So u of x is going to be f of phi of x. Is that correct? Right. If phi of x is non-negative, right? And now just set u to be constant in the complement. So this is going to be f of phi of 0 if phi of x is negative. So that's the definition, right? So in this drawing, in this picture here, the function u would be constant in this rho domain. So this is the test function, and now the goal is to estimate the Sobolev ratio, right? So we want to estimate integral of gradient of u squared dv. Here g is just my asymptotically flat metric divided by integral of u to the 6th power to the 1/3. Right, over m, where m is now AP3 minus a point. And for that, we'll see that, again, the monotonicity of the Hawking mass will play a very important role. So what's the idea? Well, we have some integrals to compute, and we have a foliation of the domain given by a function phi, into level sets of a function phi. So this reminds us of the co-area formula. Right? So that's what we have to apply here. So let me just recall the co-area formula. It just says that if I am in this setting, and if I want to integrate over the manifold some function h, for example, times the gradient of phi, right? This is going to be equal to the integral from minus infinity to plus infinity of the integral of h over the level sets of phi. Right. Okay, this is the co-area formula. It tells you how to integrate something by first integrating on the level sets and then integrating over the t parameter. So that's the formula that we want to apply. This holds for Lipschitz functions, so h has to be only integrable here, and phi could be Lipschitz. No problem with that. Okay, so let's do the calculations. So let's start then with the first integral. So you want to consider integral of gradient of u square, dvg, right? Remember that u is constant where phi is negative, so we can restrict ourselves to the set of points where phi is positive, right? No problem with that. And the gradient of u, and in that domain, the function u is just f composed with phi, right? So if you compute the gradient of that, you're going to get the derivative of f composed with phi times the gradient of phi. And then we have to square. So I get f prime of phi of x square multiplied by the gradient of phi square. Right? That's the expression. Now I use the co-area formula, right? When I use the co-area formula, remember that in the level sets of phi, right, this phi of x here is going to be constant, f prime of t. So this term I can bring it out, right? So the formula that I get is the following. I get minus infinity to plus infinity of f prime of t square. And then I have to drop one power here. I get the integral over the level set of gradient of phi. That's what the co-area formula gives me. But now remember that from the weak formulation, the norm of the gradient of phi is exactly the mean curvature of the level set, or what I call the weak mean curvature. Right? Remember that the formulation was norm of gradient of phi equal to the divergence of gradient of phi divided by norm of gradient of phi. So this is just the mean curvature. So the formula is integral over the real line of f prime of t square times the integral, this is sigma t, of the mean curvature. Right? That's the formula that we get. So see that I want to estimate this from above, right? So in order to do that, I'll have to estimate the integral of h from above. And that's the point where I use the monotonicity formula. Okay, this is what we get here. Let me explain the u to the 6 now. How do we do it? So in order to do u to the 6, we just have to be a little careful because there's no gradient of phi in the left-hand side. There's no gradient of phi here. But anyway, one can consider, if you want to be a little bit more precise, if you consider the set of points C epsilon, where the gradient of phi norm is bigger than epsilon, and phi is non-negative, for example, given a positive epsilon, the integral of u to the 6th power over m is going to be greater than or equal to the integral of u to the 6th over this set. Of course, because I'm dropping a region here. But now I apply the the co-area formula into this situation, right? So what I get is the integral from minus infinity to plus infinity of, now you recall is just f composed with phi, so phi becomes t, then I get f of t to the power 6, and then I get the integral over the set of, let's say, let me put it like this, sigma t intersected with c epsilon of the gradient of phi to the minus 1. Right? That's the formula that I get from the co-area formula. Okay, recall again, this is the inverse power of the mean curvature. So again, this is equal to f of t to the 6 times the integral of h to the minus 1. Now I can just pass to the limit as epsilon goes to 0, right? You can use the monotone convergence theorem of Lebesgue theory here, and you just get that the integral of u to the power 6 over m is going to be greater than or equal to the integral of f of t to the power 6 times the integral of h to the minus 1. Okay? Those are the two formulas that I want to consider. So now I have the integral of the inverse of the mean curvature. So what do I do with that? The idea now is that you can apply Holder's inequality. So you can apply Holder's inequality to the following situation. You consider I want to consider the integral of the function 1 over sigma t as being the integral of h to the 1/2 times h to the minus 1/2, for example. I'm just explaining the inequality that I will use there. And this is less than or equal, I get the squares, right? The square of this gives me h to the 1/2. And the square of this gives me h to the minus 1. This is just Holder's inequality. Once you square it, you get the square of the area here, less than or equal to the integral of h times the integral of h to the minus 1. Okay? So in the end, what I want to use is that the integral of h to the minus 1 will be greater than or equal to the sigma t square inverse of this guy. So when I plug this into this inequality, what I get is that the integral of u to the 6 is going to be greater than or equal to, well, the integral of f of t to the 6 over the real line. And now this guy is going to be greater than or equal to the area of sigma t square times this integral. And why is this good? Well, this is good because I want to bound this from below. But if I want to bound this from below, then I need, again, to bound from above the integral of the mean curvature. Exactly the same thing that I have to do if I want to bound this from above. So now the goal is to estimate the integral of the mean curvature from above. An important point is that we have to keep in mind what is happening in the model case. All the inequalities that I'm using here will become equalities on the model case. Right? Holder's inequality becomes an equality because in the case of Schwarzschild, the mean curvature is just a constant. Right? So I'm not dropping anything over here in the model case. Okay, so now we have to estimate the integral of the mean curvature. and that's where the monotonicity of the Hawking mass plays a role. So let me just explain that. So one key point is that the Euler characteristic of sigma of t remains less than or equal to 2. So the surface never gets disconnected once you evolve it by the flow. The idea here is that from the minimization principles that I discussed last time, this is a general fact for inverse curvature flow. You can always prove that the interior and the exterior are connected. This just follows from general principles of inverse curvature flow. So this is saying that my surface can never get disconnected, right? If it gets disconnected, then I get, for example, 2 components inside. So this is important because the monotonicity of the Hawking mass uses this fact. Maybe the genus can get higher, right? You can start with a sphere, but maybe at some point it is better to add a neck. I don't know, in the minimization principle that I talked about. But it never gets disconnected. Okay, so let me just recall the monotonicity of the Hawking mass. So the Hawking mass was defined as square root of the area divided by 16 pi the 3rd power times 16 pi minus the integral of h squared over sigma, right? And we did the calculation, right? So we have the Hawking mass of sigma of t is monotone. Let's see, is non-decreasing if sigma of t solves the inverse curvature flow. But then if it's non-decreasing, then the Hawking mass of sigma of t, let me write it down again. So I get this times this at time t is going to be greater than or equal to the Hawking mass at time 0. Right? But the Hawking mass at time 0, remember that time 0 I have a minimal surface, so this integral just disappears. Then I get the square root of the area of sigma 0 divided by 16 pi. Right? Because I have a 16 pi here. So that's the inequality that I get from the monotonicity of the Hawking mass. Now I just play around with this. Also remember that the area of the surfaces grows exponentially. It's always time, the initial area times exponential of t. Okay, so what do we get from here? So I just want to prove a proposition where the proposition is integral of h over sigma t is less than or equal to something, right? So the proof is just play with this, right? So if we rearrange this, let's see how do we do it. I can pass this guy to the right hand side, then I get 16 pi minus this integral over sigma of t greater than or equal to the square root of the area of sigma naught divided by the area of sigma t, right? But remember the exponential relation. This is just, let's see, exponential of minus t over 2, I guess, right? Okay, is that correct? Yeah, so I get that the integral of h squared is going to be at most 16 pi minus exponential of minus t over 2. But now I want the integral of h. So again, I have to apply Holder. I apply Holder's inequality once again. And I get that the integral of the mean curvature is going to be less than or equal to the integral of the mean curvature square to the 1/2 times the integral of 1 square, right, which gives me the area, to the 1/2. So this is just, let me just put it like the area to the 1/2. So let me just use this space here to finish. Okay, so if I use this here, right, I get that this is going to be greater than or equal to the, I can put a square over here, square, this disappears, and this disappears, right? Then I get that this is greater than or equal to the integral of the mean curvature square over sigma of t divided by the area of sigma t. Right? Less than or equal to 16 pi minus the exponential of minus t over 2. Right? Is that correct? I think so. So finally, what I get then is that the integral of the mean curvature over sigma of t is less than or equal to the square root of, this is exponential t times the original area multiplied by this. So let me check if I have the correct formula. There's the 16 pi should be outside, right? Yeah, that's correct. So where's the original mistake here? First line. Oh, I see. Right. There's a 3 and there's a 1 here. Right. Yeah. So there's something missing. So let's see. Then I should get a 16 pi here, right? Thanks. So I get this, right? Yeah. So there's 1 minus this. And 1 minus this. 1 minus this times 16 pi. Right, so now the formula is correct. So let me just write it over here. Square root of the 16 pi times the initial area. Then I get exponential of t minus exponential of t over 2. So that's the estimate that I get from the monotonicity of the Hawking mass. And again, I'm not losing anything in the model case. Schwartz to the mean curvature is a constant. I get equalities everywhere. So now I just have to combine everything that I wrote to estimate the Sobolev ratio. So let's see. I want to use this, right? And this. Okay. So what I have is that the Sobolev constant applied to u to the 6 to the power 1/3 is going to be less than or equal to, well, the numerator is going to be bounded by the integral of f prime of t squared, right? Then I get the integral of the mean curvature, but the integral of the mean curvature is at most this. So I get the square root of 16 pi initial area times exponential of t minus exponential of minus of t over 2. That's for the numerator. And the denominator is greater than or equal to this thing to the power 1/3. Right? So what do I have then? I will have everything is going to be to the power 1/3, right? Integral of f of t to the 6. So sigma t squared is just the exponential 2t times the original area, right? Then I have the inverse of the integral of the mean curvature. The integral of mean curvature is less than or equal to this. When I take the inverse, I get a greater than or equal to inverse of this guy. So I get, right, so I get the inverse of that. Here I have a square, right? Because I have area square. So when I get minus 1 over there, I have the following. 16 pi area of sigma naught exponential of t minus exponential of t over 2 to the minus 1/2. No, sorry. Minus 1/2. Right? Because I'm taking the inverse. So I get this awful expression over here. But the important point of this is that if you look at this carefully, you see that the original area cancels. Let's see. So I get the original area to the power 1/2 over the numerator. Here I get the original area to the minus 1/2 plus 2. I get 3/2. 3/2 to the power 1/3. I get again 1/2. So the area of sigma naught cancels. Then I can write this as, it doesn't depend on the original area. F prime of t squared square root of 16 pi times exponential of t minus t over 2 divided by this. F of t to the 6th power exponential to t 16 pi exponential t to the minus 1/2 everything to the power, well, the whole integral to the power 1/3. Well, I can give you the explicit expression of f of t just for, so let me just put f of t here. You can compute because it comes from the model. Right? Twice exponential of t minus exponential of t over 2. And now you have the apparently difficult task of computing this integral. Right? I give f of t. I would have to compute these integrals if I want to get the constant. Right? So it looks kind of impossible. But now it comes the nice observation that if I was working with the model, everything would be equality. Right? The model is Schwarzschild. So I'm not losing anything, just applying Holder to constant functions. So since everything would be equality, this thing has to be sigma 2 over 8 because it comes from the model case. And that's the proof. Right? I construct a test function such that the Sobolev ratio is less than or equal to sigma 2 over 8. And this proves the theorem of Bray and Nevis. Let me just remind that the corollary of this, from what we discussed last time, is that the sigma invariant, the Amabe invariant of RP3 is just sigma 2, which is Bray and Nevis. Okay, so this finishes the second part of the mini course. So now we get to the third part, where I have to be a little brief because of time. So again, the topic of the mini course is geometric applications of curvature flows. So in the third part, I'm going to talk about the rigidity of RP3 with respect to area minimizing surfaces, area minimizing projective planes, and I just mention, if time permits, I'll mention the Menus conjecture. Okay, so what's the situation now? So the problem that I want to consider is the following. Suppose I have a compact 3 manifold, M3, compact, with a given metric. And I'm going to assume that this manifold contains embedded projective planes. So I'm going to assume that there exists, that this is the topological assumption on M. Right? Assumption. There exists an embedded surface. Embedded surface, sigma 2, contained in M3, diffeomorphic to a projective plane, RP2. So the example, of course, class is RP3. Right? The equator of RP3 is an embedded projective plane. So then, if I have such a manifold, then I can look at the following problem. I look at all the embedded projective planes. So let me denote by F this collection of surfaces. This is going to be the collection of all sigma 2's in M, such that sigma 2 is an embedded projective plane. Of course, from my topological assumption, I know that this collection is not empty, right? Then I just minimize area over all these surfaces. I consider the following invariant, defined by this definition. I define of A of mg to be the infimum of the areas over all surfaces in the collection. Right? I look at all the projective planes, minimize area. That's a number, positive number. So this has to be a positive number because if the area could be arbitrarily small, then the surface would have to fall into a small ball, and we know that balls don't have embedded projective planes. Right? R3 doesn't have this property. So this has to be a positive number. Let me just discuss an example. Suppose again I work with RP3 with the standard metric. So G0 is the metric with constant curvature. 1, for example. Well, it's not totally easy, but it follows from that. So one can see this from general arguments of triangulations, and that Well, in this case, I guess it follows from the monotonicity of the ratio area of, minimal surfaces obey a monotonicity formula. Right? So with the radius. So yeah, so right, that's a good point. So we're going to minimize this. No, actually, right, so let me think about this. Right. Yeah, I think that if you have an arbitrarily small, if you have a surface with very small area, you can prove that it has to bound something. Right? And for example, here you know that the projective plane cannot bound anything, for example. Right? You can work with, there's an argument in Mix-Simon-Yau with works with triangulations. So if the area is very small, you can sort of make the surface transversal to the dual triangulation, and follows that it has to bound the domain, right? Which is not the case here. Yeah, I need to know that it's positive, because then I want to minimize the area, and then I want to get the minimal surface from that. But it follows from, again, this paper of Mix, Simon, and Yau. No, but on a compact 3 manifold, there's always a positive epsilon, such that if the area is less than epsilon, then it has to bound. That's what I'm saying, that it follows from Mix, Simon, and Yau. Yeah, for compact 3 manifolds. Okay. So right, so this number is positive. Then I want to minimize area in the class, right? So let me just finish what I was discussing here. G naught is a metric of constant curvature 1. The scalar curvature here is 6, right? Which is just n times n minus 1. I'm in 3 dimensions, and in this case, the minimizing has to be the equator, so the area is going to be 2 pi, right? Which is the area of the equator in the projective space. So that's just a calculation. So the theorem that I want to discuss is the following. Later I will talk about the relation with the Minus conjecture. So the theorem is due to 4 people. Let's see, Bray, Brendel, Eichmeyer, and Nevis. The theorem says the following. Suppose that you are in this situation, right? You have a compact manifold, Riemannian manifold, which admits embedded projective planes. And suppose that the scalar curvature is at least 6. If the scalar curvature of G is at least 6, then this invariant, the minimum area, has to be at most 2 pi. Right. So if you want to, if you look at the model case and you increase the scalar curvature, the area of the minimizing projective plane should go down. Right. This holds for any metric with this assumption of the scalar curvature. And the equality case, the equality is the only part where a flow needs to be used. The equality holds if and only if the manifold is isometric to the projective space. With a constant curvature 1 metric. So you get rigidity of the projective plane in terms of this invariant, which considers minimizing projective planes. So that's the theorem that I want to discuss. And actually, the proof of the rigidity uses Ricci flow. which is kind of interesting. So let's see, I have 25 minutes left. So let me discuss the sort of sketch the proof of this. Well, first of all, it follows again from Meek, Simon, and Yao that this infimum is realized by a projective plane. There's always a projective plane which achieves the minimum. So again, Meek, Simon, Yao. Implies that there exists sigma 2 in the collection with area of sigma equal to the infimum. Okay? The idea is that, so Meek, Simon, Yao, they consider minimizing surfaces, right? And in that spirit, they prove that that in the limit you get a disjoint union of minimal surfaces, and the genus can only go down, right? So you would have possibly only spheres and projective planes. But the point here is that these surfaces are obtained by the original sequence by cutting out, for example, long and small necks. And every time you do something like this to a projective plane, this is something analogous to a surgery. Right? Every time you do this to a projective plane, at least one of the components that you get has to be still a projective plane. So by that way, you can prove that in the limit that you get, at least one of the components is a projective plane, and of course has to achieve the area. Right? In the end, you get that in the limit there is only one projective plane and no spheres at all, by Meek, Simon, and Yao. Okay, so this is a minimization procedure. Okay, so we can work with this projective plane. And now this projective plane is going to be stable, right? So for any variation, since it's minimizing, so sigma 2 is minimizing, area minimizing. In the homology class, for example, right, implies that it's stable. So you have this guy over here, sigma, for any vector field x in the normal bundle. If you look at the variation of sigma along this vector field, you always get that the first derivative of the area is going to be 0, but the second derivative is going to be non-negative because sigma is minimizing. And that's the formula that we want to use. We just have to be a little careful because we don't know whether sigma is one-sided or two-sided. It depends on the given ambient manifold. But anyway, let me just write down the formula, the second variation formula. So if x, let's see. So if x is a section of the normal bundle of sigma, then the second derivative of the area of the corresponding variation, right, at time 0 is just the integral of gradient of x squared minus a squared plus Ricci times x squared. Nu is just the unit normal to the surface. Right? Maybe if the surface is one-sided, maybe the normal vector doesn't make sense globally, right? But it makes sense locally, so you can still talk about the Ricci curvature in the normal direction. So we know from stability that this is non-negative for any x. And that's the condition that we want to explore, to exploit, right? So the case 1 we divide the proof into two cases. Or first of all, let me write the proposition. The proposition is that the integral of a squared plus Ricci over the surface is at most 4 pi. That's what I want to prove. And the proof is divided into two cases. Case 1 is when sigma is two-sided. Two-sided means that, or intuitively, that there are two well-defined sides of the surface. Right? Precisely means that there is a continuous unit normal vector everywhere. So if sigma is two-sided, we know that there exists nu of x section of the normal bundle, unit everywhere. Everywhere and continuous. Well, this is the easy case, because if there is a well-defined normal vector, then we can just choose x to be the constant function 1 times nu as the variation. This is the simplest variation that one can consider, given by parallel surfaces. So in that case, you just choose x to be the normal vector itself, right? And then the calculation gives you that this is going to be 0, right? Because x is parallel. So here what I mean is that if you write x is a function times nu, this is gradient of f squared. That's my notation. So I get 0 over here. Then I get that this implies the integral of, by choosing this, we get that integral of a squared plus Ricci over sigma is less than or equal to 0, which of course is less than or equal to 4 pi. So this is the easy case, right? Yeah, I'm not putting hypothesis on the ambient space, right? So here in the theorem, I'm not assuming that M is diffeomorphic to RP3. I just assume that it contains embedded projective planes. So you can pick RP3, maybe do a connected sum with something which is non-orientable, something like this. You can consider, for example, RP2 cross a circle, right? There is an RP2 which is two-sided in that case. Right. Yeah, it does. Even the product metric, right? RP2 has constant curvature 1, for example. You just look at the product metric. But it never, the theorem applies, but the equality will never be achieved. It can only be achieved for RP3. Right. So case 2, which is the most interesting, is when sigma is one-sided. Right. So in that case, what you do, there is no unit normal vector field, but what you can do is that you can lift the sigma to a sphere. Right? So let me just draw a diagram. So you have sigma maybe embedded into my manifold M. Right. Now I have S2 over here. I have this standard projection, right? And I just define phi hat to be phi composed with pi. I just lift the embedding to S2. So now it's not an embedding anymore because the antipodal points are going to be sent into the same image. But now if I can look at the normal bundle, I can bring the normal bundle to S2 by the pullback, right? And because the surface is one-sided, you can see that on S2, let me just. So from the fact that sigma is one-sided, we get that there exists a section, right? Which is a section of the pullback by phi hat of the normal bundle of sigma, right? With the following properties. Nu is unit everywhere. And now nu of x is equal to minus nu of minus x. This follows easy from considerations of the fundamental group, right? So you start with a normal, then when you will go a loop to the antipodal point, you get minus the normal when the surface is one-sided. Okay, so let me just see if the notation. Right. So just geometrically, for every point x on the sphere, right, nu of x is just a unit normal to sigma at phi hat of x. So now what you do is that you define, so this vector field is, let's say is odd, right, as a function of the sphere. But then if you multiply this by an odd function, you get an even vector field. And that's what you do. So right. So let me recall the uniformization theorem. Uniformization theorem gives me that the pullback of the metric, right, phi hat star of G, is conformal to a constant curvature metric, right? I can even do it here on phi. Maybe I should do it on phi. Phi star of G is conformal to a round metric on the projective plane. This is diffeomorphic to a projective plane. So it's conformal to, let's say, I will denote by G naught, constant curvature. 1, for example. So I can think of this S2 as contained in R3 as the unit inclusion, right? Then I just define Vj of x as being, I look at, so I have S2, then I have x1, x2, and x3, the coordinates. For each j from 1 to 3, I define Vj of x to be xj times the normal. Okay? This is called the Hirsch technique. Hirsch technique. The Hirsch technique is based on the fact that I want to use the stability inequality, but in order to use the stability inequality, I have to construct test functions or test vector fields. So the Hirsch technique is based on using the uniformization theorem to construct such test functions. And now the observation is that because xj is also odd, that vj of x is equal to vj of minus x. And this says that vj makes sense as a section of the normal bundle of the surface itself. It descends to the surface. Then I can consider vj as a variational vector field for my inequality over here. So when you do this, I have to use all three of them. So choosing x to be vj, we get that the integral over the, let's see, over the sphere, over the projective plane, right, of what I was denoted by gradient of vj square minus a square plus Ricci nu times the normal vj square. This is always non-negative for each j from 1 to 3. Okay? But then let me just rewrite this. This implies that the integral of a square plus Ricci times the normal vj square is going to be less than or equal to this. But this is just the integral of the gradient of the function xj square over sigma, right? And now I use the conformal invariance of the Dirichlet energy in dimension 2. Right? So the integral of, let me just write. Maybe, I'm not sure if Zindin talked about this, but maybe he did, or it follows from what he said, that the gradient of some function phi square in the metric G is equal to this, the metric G prime, if G and G prime are conformal, and of course in dimension 2. Dimension of the surface has to be 2. This integral is a conformal invariant. So I can just replace the metric G here by the constant curvature metric that I'm using. So when you do this, I get actually 1/2 of the integral over the sphere, right? Because I have a cover here of gradient of xj square with respect to G naught. This is now the standard metric over the sphere. And then you just compute this. It's easy to see that this is going to be equal to the integral of xj square. Now I just take the sum as j varies from 1 to 3, and then I get, as I take the sum as j goes from of 1 to 3, I get this, a square plus Ricci nu times this guy is less than or equal to the sum of this xj square dv G naught over S2. But the sum of the squares is 1, right? So I get the area of the round sphere, which is 4 pi. And now the sum of these vectors is also 1, right? Because the norm of Vj is exactly xj square. So the sum of Vj square is also 1, so I get the integral of a square plus Ricci nu is less than or equal to 4 pi, which is what I wanted to prove. And that's exactly what happens in the model case. In the model case of RP3, we get that the projective plane is totally geodesic, and that the Ricci curvature is 2, for example, right? And then you get this inequality. Okay, I have 10 minutes left. Let me summarize what are the main steps now. So we proved this proposition, that the integral of a square plus Ricci is at most 4 pi, right? So now we use Gauss' equation to derive an estimate on the area of the surface. I can do this very quickly. So now remember the Gauss equation. Gauss equation gives me that the scalar curvature is equal to twice the Ricci curvature in the normal direction plus twice the Gauss curvature of the surface plus a square minus h square. So, right. So my goal is to get rid of the Ricci curvature over here, right? So I get that the integral of, that implies that integral of a square plus, instead of Ricci curvature here, I will replace by the formula that I get from the Gauss equation. Then I get 1/2 of the scalar curvature minus the Gauss curvature minus 1/2 of norm of a square plus 1/2 of h square. I know that this is at most 4 pi, right? But now this tells me that the integral over the projective plane, well, this guy, the projective plane is minimal, right? So the mean curvature is 0 in that case. So I get 1/2 of norm of a square plus this guy's But remember that I'm assuming that the scalar curvature is greater than or equal to the original scalar curvature, which is 6. So the scalar curvature is bounded by 6. So then I get 4 pi. I get 6 divided by 2. This gives me 3 times the area. Right? And the integral of the Gauss curvature by Gauss-Bonnet gives me minus 2 pi the Euler characteristic, which is 1 in the case of the projective plane. Right? This is 1. Plus 1/2 of integral of a squared. And the conclusion from here is that this guy is non-negative. Right? So this is greater than or equal to 3 times the area minus 2 pi. And from that I get that the area that the area. 3 times the area is at most 6 pi. And this was my inequality. Right? So a scalar curvature bound from below implies an upper bound on the area of an area minimizing projective plane. Just by the Hirsch technique and the Gauss equation. So let me summarize what happens for the rigidity case. I said that this uses the Ricci flow. So what you do is the following. Let me just say what are the main steps. Now I want to do the equality case. The first thing is that you do is to solve the Ricci flow. Right? So you look at this equation. It was written down here by Thomas in the first talk. You solve the Ricci flow with initial condition given by G. Then for each t, you can consider the minimum of the areas of all the projective planes for the metric G of t. Right? This is a function that you can easily prove that is Lipschitz continuous. Now I want to differentiate this function with time, right? and if you do that, what follows is that the derivative with respect to t of this area is bounded below by minus 8 pi using Ricci flow. So I can sort of explain briefly what's the idea here. The idea here is that, so for each time, there is a metric, and I can minimize area, and there is a minimizing projective plane. For each time, there's a minimizing projective plane. But maybe this projective plane is moving in a non-continuous way or something like that. So I have to be a little careful. But what I do is that I freeze the time t. I look at some time slightly smaller, t minus delta. Right? And I know that the area, let me just write this, that the infimum of the areas for this metric, G of t minus delta, because it's the infimum, right, has to be less than or equal to the area of this guy at time t with respect to the metric. This is less than or equal to the area of all projective planes. So I just freeze one of them and look at the same guy for a time slightly earlier. I get this. Right? So basically when you compute the derivative of this, you're going to get that. So this is a time earlier, right? So when you look at the definition of the derivative, you get a minus sign over here. So when you differentiate, you get greater than or equal to the derivative of this area. But this is just the derivative of the area of a fixed surface when you're varying the metric. This is an easy calculation using Ricci flow. Again, use Gauss equation, Gauss-Bonnet theorem, you get minus 8 pi from that calculation. So this says that the area at time t is at least the original area minus 8 pi t, right? Because of this inequality. Now you use maximum. Now you look at the scalar curvature. Right? The evolution equation of the scalar curvature through Ricci flow is like this. This is very classical. Use the Cauchy-Schwarz inequality on this term, and you get this is bounded below by 2/3 of scalar curvature square. Right? And now if you use the maximum principle for the scalar curvature, you get that the infimum of the scalar curvature at time t is going to be greater than or equal to, let me just write the formula, 1 over the infimum at time 0 minus 2/3 of t. Well, why this? Because this is exactly the function that solves the ODE if I drop the Laplacian and have equality here. This is exactly the function that solves the ODE. Right? But now I assume that the scalar curvature initially was at least 6. Right? This is just maximum principle. So then this is going to be greater than or equal to, if you do the calculation, 6 to the 1 minus 4t. That's what you get from maximum principle. And now remember that we proved that if the scalar curvature was greater than 6, right, the area would be less than 2 pi. That's what we proved, right? Well, if the scalar curvature is positive, by scaling, I can always suppose that the scalar curvature is at least 6, just scaling the metric. So if you write, I could rephrase this equivalently. Instead of assuming that the scalar curvature is at least 6, I can write in such a way that I drop this assumption, and then the inequality would become the infimum of the scalar curvature times this is always less than or equal to 6 times 2 pi, which is 12 pi. Okay, this is the scale invariant way of phrasing the same result. So that's what we proved. Now if you use these formulas and this, you get that, well, the infimum of scalar curvature at time t times the area of g of t will be greater than or equal to, well, I'm assuming the equality case. In the equality case, this guy is going to be 2 pi. Right? So I get 2 pi minus 8 pi t times that. 6 divided by 1 minus 4t. So if you do the calculation, this is easily 12 pi. Right? On the other hand, we know that this is less than or equal to 12 pi. So you get equality. If you have equality, you just look at the maximum principle. You get automatically that the trace-free part of the Ricci curvature has to be 0. That's what we are dropping when I wrote this in the quality. So this implies, by maximum principle, that the trace-free part of Ricci is 0. In other words, G is Einstein. But we are in dimension 3, right? In dimension 3, Einstein implies constant curvature. And then there's a little topological argument to make sure that the quotient is RP3 and not other quotient. Right? I don't have time to discuss this. But this proves that the manifold is isometric with some topological argument of RP3 times G naught. Okay, just say in 2 sentences what the Minus conjecture was. Well, so we proved that if there is an area minimizing surface of area 2 pi, assume that the scalar curvature is at least 6. We proved that it is isometric to the projective space. So you can ask, what if instead of minimizing, you just ask that the surface is stable? Right? Is it stable enough? And actually it's not. So this is related to the Minus conjecture. Unfortunately, I do not have time to say. I'm just going to finish. I'm just going to draw a picture. So this is a theorem of Brendel, myself, and Neves. So we constructed a metric on Sn, which looks like this on Sn plus. For each n greater than or equal to 3, that in a small neighborhood of the equator, this metric is exactly the standard metric. And here does something funny, but such that the scalar curvature is always bigger than or equal to n times n minus 1 everywhere, and such that at some point, this is everywhere, and such that at some point you have the strict inequality somewhere. So in other words, it's possible to push the scalar curvature up of the hemisphere without changing the metric near the equator. So if you look at this metric and then you identify, this was a counterexample to the Minus conjecture. So Minus conjecture was that any such metric would have to be isometric to the standard. So if you identify antipodal points on the boundary, you get a metric on the projective space, which has, let's say in dimension 3, which has a projective plane of exactly area 2 pi in that case, but it's not isometric. And it's stable because locally it's the same thing. Well, the explanation is that it's stable, but it's not area minimizing. Okay, sorry about the time. Let me finish here. Thanks.